In complex analysis, a complex logarithm function is an inverse of the complex exponential function, just as the real natural logarithm lane x is the inverse of the real exponential function x. Thus, a logarithm of a complex number z is a complex number w such that u equals z. The notation for such a w is lane z or log z. Since every non-zero complex number z has infinitely many logarithms, care is required to give such notation an unambiguous meaning. If z equals r theta with r greater than 0, then w equals lane r plus I theta is one logarithm of z. Adding integer multiples of 2 pi I gives all the others. Problems with inverting the complex exponential function. For a function to have an inverse, it must map distinct values to distinct values, i.e., be injective. But the complex exponential function is not injective, because u plus 2 pi I equals u for any w. Since adding I theta to w has the effect of rotating u counterclockwise theta radians. Even worse, the infinitely many numbers forming a sequence of equally spaced points along a vertical line are all mapped to the same number by the exponential function. So the exponential function does not have an inverse function in the standard sense. There are two solutions to this problem. One is to restrict the domain of the exponential function to a region that does not contain any two numbers differing by an integer multiple of 2 pi I. This leads naturally to the definition of branches of log z, which are certain functions that single out one logarithm of each number in the domains. This is analogous to the definition of arcsine x on -1, 1, as the inverse of the restriction of sin theta to the interval minus pi 2, pi 2. There are infinitely many real numbers theta with sin theta equals x, but one chooses the one in minus pi 2, pi 2. Another way to resolve the indeterminacy is to view the logarithm as a function whose domain is not a region in the complex plane, but a Riemann surface that covers the punctured complex plane in an infinite to one way. Branches have the advantage that they can be evaluated at complex numbers. On the other hand, the function on the Riemann surface is elegant in that it packages together all branches of log z and does not require an arbitrary choice as part of its definition. Definition of principal value. For each non-zero complex number z equals x plus y, the principal value log z is the logarithm whose imaginary part lies in the interval at and 2. Then the principal value of the logarithm can be defined by, for example, log equals lane 3 minus pi I 2. Another way to describe log z is as the inverse of a restriction of the complex exponential function, as in the previous section. The horizontal strip S consisting of complex numbers w equals x plus y such that minus pi less than y pi is an example of a region not containing any two numbers differing by an integer multiple of 2 pi I. So the restriction of the exponential function to S has an inverse. In fact, the exponential function maps S bijectively to the punctured complex plane, and the inverse of this restriction is. The conformal mapping section below explains the geometric properties of this map in more detail. When the notation log z appears without any particular logarithm having been specified, it is generally best to assume that the principal value is intended. In particular, this gives a value consistent with the real value of lane z when z is a positive real number. The capitalization in the notation log is used by some authors to distinguish the principal value from other logarithms of z. Not all identities satisfied by lane extend to complex numbers. It is true that log z equals z for all z0, but the identity log ez equals z fails for z outside the strip S. For this reason, one cannot always apply log to both sides of an identity z equals u to deduce z equals w. Also, the identity log equals log z1 plus log z2 can fail. The two sides can differ by an integer multiple of 2 pi I, for instance, but the function log z is discontinuous at each negative real number, but continuous everywhere else in To explain the discontinuity, consider what happens to argz as z approaches a negative real number a. If z approaches a from above, then argz approaches pi, which is also the value of argA itself. But if z approaches a from below, then argz approaches minus pi, so argz jumps by 2 pi as z crosses the negative real axis, and similarly log z jumps by 2 pi I. Branches of the complex logarithm. Is there a different way to choose a logarithm of each non-zero complex number so as to make a function L that is continuous on all of? Unfortunately, the answer is no. To see why, imagine tracking such a logarithm function along the unit circle, by evaluating L at a theta as theta increases from 0 to 2 pi. For simplicity, suppose that the starting value L is 0. Then for L to be continuous, L must agree with I theta as theta increases. In particular, L equals 2 pi I, but E2 pi I equals 1, so this contradicts L equals 0. Because one of the goals is to be able to differentiate the function, it is reasonable to assume that the function is defined on a neighborhood of each point of its domain. In other words, U should be an open set. Also, it is reasonable to assume that U is connected, since otherwise the function values on different components of U could be unrelated to each other. All this motivates the following definition. A branch of log z is a continuous function L defined on a connected open subset U of the complex plane such that L is a logarithm of z for each z in U. For example, the principal value defines a branch on the open set where it is continuous, which is the set obtained by removing 0 and all negative real numbers from the complex plane. Another example. Once a branch is fixed, it may be denoted log z, if no confusion can result. Different branches can give different values for the logarithm of a particular complex number, however, so a branch must be fixed in advance in order for log z to have a precise unambiguous meaning. Branch cuts. The argument above involving the unit circle generalizes to show that no branch of log z exists on an open set U containing a closed curve that winds around 0. To foil this argument, U is typically chosen as the complement of a ray or curve in the complex plane going from 0 to infinity in some direction. In this case, the curve is known as a branch cut. For example, the principal branch has a branch cut along the negative real axis. If the function L is extended to be defined at a point of the branch cut, it will necessarily be discontinuous there. At best it will be continuous on one side, like log z at a negative real number. The derivative of the complex logarithm each branch L of log z on an open set U is an inverse of a restriction of the exponential function, namely the restriction to the image of U under L. Since the exponential function is holomorphic with non-vanishing derivative, the complex analog of the inverse function theorem applies. It shows that L is holomorphic at each z in U, and all equals 1 z. Another way to prove this is to check the Cauchy-Riemann equations in polar coordinates. Constructing branches via integration, the function lane x for ex greater than 0 can be constructed by the formula if the range of integration started at a positive number other than 1. The formula would have to be instead. In developing the analog for the complex logarithm, there is an additional complication. The definition of the complex integral requires a choice of path. Fortunately, if the integrand is holomorphic, then the value of the integral is unchanged by deforming the path. And in a simply connected region U, any path from A to Z inside U can be continuously deformed inside U into any other. All this leads to the following. If U is a simply connected open subset of not containing 0, the complex logarithm is a conformal map. Any holomorphic map satisfying for all is a conformal map, which means that if two curves passing through a pointer of U form an angle alpha, then the images of the two curves form the same angle alpha at F. Since a branch of log z is holomorphic, and since its derivative 1, z is never 0, it defines a conformal map. For example, the principal branch W equals log z, viewed as a mapping from to the horizontal strip defined by im z less than pi, has the following properties, which are direct consequences of the formula in terms of polar form. Circles in the z-plane centered at 0 are mapped to vertical segments in the w-plane connecting a minus by I to a plus by I, where a is a real number depending on the radius of the circle. Rays emanating from 0 in the z-plane are mapped to horizontal lines in the w-plane. Each circle and ray in the z-plane as above meet at a right angle. Their images under log are a vertical segment and a horizontal line in the w-plane, and these two meet at a right angle. This is an illustration of the conformal property of log. The associated Riemann surface construction. The various branches of log z cannot be glued to give a single function because two branches may give different values at a point where both are defined. Compare, for example, the principal branch log on with imaginary part theta in and the branch L on whose imaginary part theta lies in. These agree on the upper half plane, but not on the lower half plane. So it makes sense to glue the domains of these branches only along the copies of the upper half plane. The resulting glued domain is connected, but it has two copies of the lower half plane. Those two copies can be visualized as two levels of a parking garage, and one can get from the log level of the lower half plane up to the L level of the lower half plane by going 360 degrees counterclockwise around 0. First crossing the positive real axis into the shared copy of the upper half plane and then crossing the negative real axis into the L level of the lower half plane. One can continue by gluing branches with imaginary part theta in, and so on, and in the other direction, branches with imaginary part theta in, and so on. The final result is a connected surface that can be viewed as a spiraling parking garage with infinitely many levels extending both upward and downward. This is the Riemann surface R associated to log z. A point on R can be thought of as a pair where theta is a possible value of the argument of z. In this way, R can be embedded in the logarithm function on the Riemann surface because the domains of the branches were glued only along open sets where their values agreed. The branches glue to give a single well-defined function. It maps each point on R to lane z plus I theta. This process of extending the original branch log by gluing compatible holomorphic functions is known as analytic continuation. There is a projection map from R down to that flattens the spiral, sending to Z. For any, if one takes all the points of R lying directly above Z and evaluates log at all these points, one gets all the logarithms of Z. Gluing all branches of log z instead of gluing only the branches chosen above, one can start with all branches of log z, and simultaneously glue every pair of branches in along the largest open subset of on which L1 and L2 agree. This yields the same Riemann surface R and function log as before. This approach, although slightly harder to visualize, is more natural in that it does not require selecting any particular branches. If U is an open subset of R projecting bijectively to its image U in, then the restriction of log to U corresponds to a branch of log Z defined on U. Every branch of log Z arises in this way. The Riemann surface as a universal cover. The projection map realizes R as a covering space if, in fact, it is a Galois covering with deck transformation group isomorphic to, generated by the homeomorphism sending to, as a complex manifold. R is biholomorphic with via log. This shows that R is simply connected, so R is the universal cover of applications. The complex logarithm is needed to define exponentation in which the base is a complex number. Namely, if A and B are complex numbers with a 0, one can use the principal value to define AB equals AB log A. One can also replace log A by other logarithms of A to obtain other values of AB. Since the mapping W equals log Z transforms circles centered at 0 into vertical straight-line segments, it is useful in engineering applications involving an annulus. Generalizations. Logarithms to other bases. Just as for real numbers, one can define for complex numbers A and B, the only caveat being that its value depends on the choice of a branch of log defined at A and B. For example, using the principal value gives logarithms of holomorphic functions if f is a holomorphic function on a connected open subset U of, then a branch of log f on U is a continuous function g on U such that e.g. equals f for all z in U. Such a function g is necessarily holomorphic with g equals f for all z in U. If U is a simply connected open subset of, and f is a nowhere vanishing holomorphic function on U,